Imagine a second sun in our sky. Not a distant star but a dim, warm glow hanging in the night, a constant companion to our moon. This isn't science fiction, this was almost our reality. Jupiter, the colossal king of our solar system, is what astronomers call a failed star. It possesses all the right ingredients: hydrogen and helium, the very same elements that fuel our own sun. It just never got big enough. If it had been about 80 times more massive, its core would have ignited in nuclear fusion and our solar system would have had two suns. Think about that for a moment. Our entire history, our biology, our very perception of day and night would be completely different. Jupiter isn't just a planet, it's a shadow of what could have been. This single fact changes everything. It reframes Jupiter from a distant ball of gas into a celestial entity with a story of cosmic ambition. Without Jupiter's immense gravity acting as a gatekeeper, countless asteroids and comets would have slammed into the inner planets, possibly preventing life on Earth from ever taking hold. Let's try to wrap our heads around just how big Jupiter is. You've probably heard the numbers. It's 11 times wider than Earth and has more than twice the mass of all the other planets in our solar system combined. But numbers can be abstract, so let's make it tangible. Imagine Earth is a single grape. On that scale, Jupiter would be a basketball. Now picture placing all the other planets, Mercury, Venus, Mars, Saturn, Uranus, and Neptune, side by side. Jupiter is still more than twice as massive as all of them put together. It's not just the biggest planet in the neighborhood, it is the neighborhood. Its gravitational pull dictates the orbits of asteroids, and has even been known to fling comets out of the solar system entirely. Jupiter's gravitational pull is about 2.5 times stronger than Earth's. If you could somehow stand on a platform floating in its cloud tops, you would weigh 2.5 times your normal weight. A person who weighs 150 pounds on Earth would feel like they weigh 375 pounds there. The planet's sheer scale also explains its rapid rotation. You might think a giant like Jupiter would spin slowly, but it's the fastest spinning planet in our solar system. One day on Jupiter lasts less than 10 hours. This dizzying spin has a dramatic consequence. It stretches the planet at its equator. Jupiter isn't a perfect sphere, it's an oblate spheroid, meaning it bulges out in the middle. This rapid rotation is also the engine that drives its wild weather, whipping the clouds into the distinct horizontal bands of dark belts and light zones we see in every photograph. There is a feature on Jupiter so iconic that even a child can point it out: the Great Red Spot. But calling it a spot is perhaps the greatest understatement in astronomy. This is not a spot, it is a storm, a hurricane, an anticyclone so vast that you could fit the entire planet Earth inside it with room to spare. And it's not a recent phenomenon. We have been observing this storm for at least 190 years, and historical observations from as far back as the 1660s by astronomer Giovanni Cassini may have been the very same storm. This means the Great Red Spot has been raging for longer than the United States has existed. It's a weather event on a timescale we can barely comprehend. What makes this storm so persistent? On Earth, hurricanes form over warm ocean waters and lose their energy when they make landfall. But Jupiter has no land. There is no solid surface to break the storm apart. It is a vortex feeding on the planet's internal heat and the sheer velocity of its jet streams, which can reach speeds of over 400 miles per hour. The Great Red Spot is trapped between two of these powerful jet streams moving in opposite directions, essentially rolling it along like a ball bearing between two conveyor belts. It's a self-sustaining system, a weather engine that has been running for centuries without any sign of stopping completely, though recent observations show it is shrinking. For a long time, we didn't know much about its structure. Was it a shallow feature confined to the upper clouds, or did it have deep roots? Thanks to NASA's Juno mission, which arrived at Jupiter in 2016, we now have an answer. By using microwave instruments to peer deep below the cloud tops, scientists discovered that the Great Red Spot is not just a surface-level storm. It extends more than 300 miles, about 500 kilometers, down into the atmosphere. That's 50 times deeper than the deepest part of Earth's ocean. This incredible depth helps explain its longevity. It's not just a storm, but a monumental column of swirling gas, anchored deep within the planet's churning interior. To truly understand Jupiter, you have to abandon all earthly notions of atmosphere. Our atmosphere is a thin, transparent veil. Jupiter's atmosphere is the planet itself. It's a deep, crushing ocean of gas that transitions seamlessly into a liquid interior with no clear boundary. The part we see, the colorful swirling clouds, is just the very top layer, like the foam on a cosmic latte. This visible layer is organized into three distinct cloud decks. The highest clouds, the ones that form the white and bright zones, are made of frozen ammonia ice. Below that is a layer of ammonium hydrosulfide crystals, and deeper still, a layer of water ice and vapor clouds. The vibrant colors we associate with Jupiter, the oranges, browns, yellows, and reds, are a direct result of this complex chemical cocktail. The stripes, known as zones, the lighter bands, and belts, the darker bands, are not just painted on. They are regions of rising and falling gas. The bright zones are areas where gas is rising from the warmer interior, cooling and condensing into pale ammonia ice clouds. The darker belts are regions where cooler gas is sinking, allowing us to see deeper into the atmosphere where different, more colorful chemical compounds reside. Diving deeper, the environment becomes truly alien. As you descend, the pressure and temperature skyrocket. About 60 miles, 100 kilometers below the visible cloud tops, the pressure is already 10 times that of Earth's sea level. Keep going, and the pressure becomes so immense that the hydrogen gas around you starts to behave in a way that is impossible on Earth. It stops being a gas and transforms into a supercritical fluid, a strange state of matter that is neither a true liquid nor a true gas. It has the density of a liquid but can flow like a gas, filling any container. There is no surface, no splash, just a gradual, terrifying thickening of the air around you. This is the world that NASA's Galileo probe experienced in 1995. It was the first and only probe to ever descend into Jupiter's atmosphere. For 58 minutes it plunged through the upper layers, sending back data on temperature, pressure, and chemical composition before it was inevitably destroyed. It measured winds over 450 miles per hour and found that the atmosphere was surprisingly dry, suggesting it had entered an unusual hotspot. The Galileo probe's final transmission came from a depth where the pressure was 23 times that of Earth, and the temperature was 300 degrees Fahrenheit, or about 150 degrees Celsius. It was a heroic one-way trip into the heart of the hurricane, giving us our first direct taste of the alien environment within. For nearly all of human history, we believed Earth was the center of everything. The sun, the moon, the planets, and the stars all revolved around us. It was an intuitive, comforting, and deeply ingrained worldview. But in 1610, that view was shattered by an Italian astronomer named Galileo Galilei. Using a new invention called the telescope, which he had improved himself, he pointed it toward Jupiter. What he saw over the course of several nights would spark a revolution in science and philosophy. He didn't just see the planet, he saw 4 tiny stars accompanying it, points of light that seemed to dance around Jupiter, disappearing behind it and reappearing on the other side. Galileo meticulously documented their positions night after night. He quickly realized these were not background stars. They were moving with Jupiter. More importantly, they were clearly orbiting around Jupiter. He had discovered what we now call the Galilean moons: Io, Europa, Ganymede, and Callisto. This was the first time in history that anyone had observed celestial bodies orbiting something other than Earth. It was a direct visual contradiction of the geocentric model that had dominated Western thought for over 1,500 years. If moons could orbit Jupiter, then it was possible that Earth was not the center of all motion. The universe suddenly became a much larger, more complex, and more interesting place. This discovery was more than just an astronomical observation. It was a philosophical bombshell. It provided powerful, observational evidence for the heliocentric theory proposed by Nicholas Copernicus decades earlier, the idea that Earth and the other planets revolved around the Sun. Galileo's findings were published in his short treatise Sidereus Nuncius, or Starry Messenger, which became an instant sensation and made him famous across Europe. But it also put him on a collision course with the powerful Catholic Church, which held the geocentric model as scripture. His unwavering support for a sun-centered cosmos would eventually lead to his infamous trial and house arrest. Today we can see the Galilean moons with a simple pair of binoculars, a direct link to that pivotal moment in history. Each time we look, we are recreating Galileo's revolutionary act. We are witnessing a miniature solar system that proved our own world was not the center of the universe. This shift in perspective is perhaps Jupiter's greatest gift to humanity. It didn't just teach us about another planet, it taught us about our own place in the cosmos. For centuries, our view of Jupiter was skin deep. We saw its beautiful chaotic cloud tops but could only guess at what lay beneath. That all changed on July 4, 2016, when NASA's Juno spacecraft successfully entered orbit around Jupiter. Unlike previous missions that orbited at a safe distance, Juno was designed for a daring polar orbit that would bring it incredibly close to the planet, at times just 2,600 miles above the swirling clouds. This risky maneuver was necessary to achieve its primary goal, to peer beneath the veil of Jupiter's atmosphere and map its deep interior for the first time. Juno is not just a camera, it's a suite of scientific instruments designed to measure Jupiter's gravity, magnetic field, and atmospheric composition with unprecedented precision. One of Juno's most stunning discoveries came from its gravity measurements. By flying so close, the spacecraft could detect tiny wobbles in its orbit caused by the uneven distribution of mass inside the planet. This data allowed scientists to create a map of Jupiter's gravitational field. They found that the famous belts and zones, the stripes we see on the surface, were not just a thin weather phenomenon. They extend deep into the planet, to a depth of about 1,800 miles. At this depth, the pressures are so extreme that the atmosphere begins to behave like a uniform, rotating fluid, and the striped pattern finally disappears. Juno showed us that Jupiter's weather is not just skin-deep, it's a fundamental part of the planet's structure. JunoCam, the mission's public outreach camera, has delivered some of the most breathtaking images of another world ever captured. Because of its polar orbit, Juno has given us our first clear views of Jupiter's poles. And they look nothing like the rest of the planet. Instead of the familiar stripes, the poles are a chaotic cluster of massive Earth-sized cyclones churning in geometric patterns. The North Pole has a central cyclone surrounded by 8 others, while the South Pole has a central cyclone surrounded by 5. These storms are incredibly stable, barely moving over the years Juno has been observing them. Why they arrange themselves in these beautiful polygonal shapes is a complete mystery that has planetary scientists scratching their heads. Perhaps Juno's most important task is to solve the mystery of Jupiter's core. Does it have a solid rocky core like Earth, or is it just gas all the way down? Early data from the mission suggests a surprising answer that is somewhere in between. Instead of a small, dense, well-defined core, Jupiter may have a large, fuzzy or dilute core. This means that heavy elements are not neatly separated at the center, but are mixed into the deep hydrogen atmosphere over a vast region, perhaps extending to nearly half of Jupiter's radius. This discovery challenges our leading models of planet formation, and suggests Jupiter's early history may have been far more violent and complex than we ever imagined. We are familiar with the northern and southern lights on Earth, the beautiful curtains of light that dance in our polar skies. These auroras happen when charged particles from the sun are funneled by Earth's magnetic field and slam into atoms in our upper atmosphere. Jupiter also has auroras, but they are on a scale that dwarfs our own. They are hundreds of times more powerful and thousands of times larger than Earth's. They are permanent fixtures at Jupiter's poles, glowing in ultraviolet and X-ray light that is invisible to the naked eye. This is a light show so immense that the energy it releases could power all of human civilization. What makes Jupiter's auroras so different is their power source. While Earth's auroras are largely controlled by the solar wind, a stream of particles from the sun, Jupiter's are mainly powered by itself. Because of its incredibly rapid 10-hour rotation, Jupiter's powerful magnetic field spins with it, acting like a colossal electric generator. It sweeps up particles that are spewed out by its volcanically active moon, Io. This moon constantly ejects about 1 ton of sulfur and oxygen per second into space, forming a donut-shaped cloud of plasma called the Io plasma torus. Jupiter's spinning magnetic field then grabs these particles and accelerates them to incredible speeds, slamming them into its own atmosphere. The result is a spectacular, non-stop aurora that is fundamentally different from ours. It's a closed-loop system. Jupiter is essentially powering its own light show using material from one of its moons. This creates a complex and dynamic interaction between the planet, its magnetic field, and its satellites. The Hubble Space Telescope has captured stunning images of these auroras, revealing not just a main oval of light, but also faint spots of light within it. These spots are the magnetic footprints of the Galilean moons. As Io, Europa, and Ganymede orbit, they create electrical currents that flow along Jupiter's magnetic field lines, creating their own small, secondary auroras when they hit the atmosphere. Juno's close passes over the poles have given us an unprecedented look into this process. Its instruments can directly sample the particles and fields responsible for these cosmic light shows. Scientists are using Juno's data to understand the mysterious mechanisms that accelerate these particles to such high energies. For example, Juno has observed powerful electron beams shooting down into the atmosphere, creating what are called discrete auroras. Understanding this massive particle accelerator can not only tell us about Jupiter, but also help us understand similar processes happening at distant stars and other astrophysical objects throughout the universe. Jupiter's ghostly lights are more than just beautiful, they are a key to unlocking some of physics' biggest questions. Despite centuries of observation and decades of robotic exploration, Jupiter remains a planet of profound mysteries. Each new discovery seems to open up a dozen new questions. We have sent probes into its atmosphere and have a spacecraft mapping its every feature, yet some of the most fundamental questions about the gas giant are still unanswered. The Juno mission has rewritten our understanding of its interior, its weather, and its poles. But the story is far from complete. Jupiter guards its deepest secrets well, challenging us to look closer, think harder, and build better tools to unravel its complexities. One of the most basic unanswered questions is, how much water does Jupiter have? Water, in the form of oxygen, is a key ingredient in planet formation models. The amount of water in Jupiter's atmosphere would tell us a great deal about where in the early solar system Jupiter formed before migrating to its current orbit. Was it formed closer to the Sun, or much farther out in the cold depths of space? The Galileo probe found surprisingly little water, but it descended into an unusually dry spot. Juno's microwave radiometer is designed to measure water deep below the clouds, but the initial data has been complex and difficult to interpret. The answer to this simple question remains tantalizingly out of reach. Another major puzzle is the source of the planet's internal heat. Jupiter radiates nearly twice as much heat into space as it receives from the Sun. Some of this is leftover heat from its formation 4.5 billion years ago, a slow, steady cooling process, but that doesn't seem to account for all of it. Could there be other processes at work in its deep interior? Some scientists have proposed that helium rain could be the answer. Deep inside the planet, under immense pressure, helium might be condensing into droplets and raining down through the liquid metallic hydrogen, releasing gravitational energy as heat in the process. Juno's data may help confirm or deny this exotic idea. Future missions are already being dreamed up to tackle these lingering questions. A dedicated atmospheric probe, a successor to Galileo, could plunge deep into a more representative part of the atmosphere to finally measure its true composition. Orbiters designed to study the Galilean moons, like the European Space Agency's JUICE mission, launched in 2023, and NASA's Europa Clipper, launching in late 2024, will also study Jupiter's environment in great detail. They will explore the intricate dance between the planet and its moons, helping us understand the system as a whole. The 10 minutes you spent reading this may have changed how you see Jupiter, but the next 10 years of exploration promise to change it all over again.